All right, so part A, let b y equal bt be the solution to the differential equation above with the initial condition at 0, the bird weighed 20 grams, which you're already kind of getting that. So part A, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. All we have to do is just plug it in because, yeah. So let's see here. We have at, so dB dt at g, capital B equals 40. And dB, we're looking at the rate. We don't know if they're gaining weight faster, so we're actually looking at the rates in each situation, so 40 and 70, and that is just 1/5 of 100 minus 40, and 1/5 of 100 minus 70, which would give you the rate 1/5 of 60. So what's 1/5 of 60? 12. And 1/5 of 30, which is 6. So that means that when it weighs 40 grams, it's gaining more, it's actually gaining weight faster because the rate of which it's gaining is 12 units per whatever unit of time. Okay.
Graph like this? Yeah. Because like when they go
I mean,
outside. It would go through the point, but then it would also go through the base. If you extended it, it would
if you extend any, it's tangent at a point, not tangent to the whole thing. Yeah. So yeah, most our functions, no matter what you have, it'll be. I think we talked about it. Whenever the point of tangency actually crosses, you have an inflection point there. So yeah. Um, so yeah, we're at this. The bird is gaining weight faster at b equals 40 because dB dt at b equals 40 is greater than the rate of change when the weight is 70. Questions on part A? Part A is not bad. All right, let's look at part B. So that's part A. So part B. Find D, all right, in terms of B, use to explain why the graph of B cannot resemble the following graph. It's the third time somebody's asked me that. There you go. So it's a maybe Tuesday. Okay, it won't be Wednesday because Wednesdays are always short days. It won't be this week. It'll be next week sometime. Not on a Monday because I hate Monday tests. So it'll be Tuesday or Thursday or Friday, one of those.
So are we just reviewing what they know?
Probably, yeah. But what they're looking for? They're looking for the d squared. Basically, what does that mean? By the way, d squared b over dt squared. We want the second derivative. All right. So what's the derivative of the derivative? Well, they gave us the first derivative, right? We actually have the first derivative. So what's the derivative? What is the derivative of 1/5 of 100 minus b? Well,
Negative 1.
negative 1/5. Yeah, because if you distribute through and then do the derivative, you just get negative 1/5, right? So that means that, well, you have to be careful here. D squared b, let's write this, so d squared b over dt squared is equal to negative 1/5 times db d squared. So we took the derivative of the rate of change and we're going to multiply it by the function itself. So that's going to give you what? Negative 1/5 times 1/5 of 100 minus b, which equals negative 1/25 of 100 minus b.
Why does it multiply by dv plus c?
Hmm?
Why does it multiply negative 1/5 by dv plus c? Like right after.
Yeah. No, I know. Trying to find words. Is dB dt the function itself? No. What is it? It's the rate. Now, being that derivatives are used to find the instantaneous rate of change, taking the second derivatives allowed us to find the rate of change of the rate of change, right? So in order to find, we cannot just say that the second derivative is just going to be negative 1/5, because that's just the derivative of the rate. So what we did is we took that rate and multiplied it by the original rate. So the derivative of the rate times the rate. Negative 1/25 of 1 minus b. Yeah, that's what we're going to do. So, let's see here. It gives you the equation for the rate of, for the rate of the second derivative. It should give you the equation for the rate of the second derivative. So if I did solve for dB dt in that case, I would have the equation for the second derivative. All right. So the second, oh, you guys got to go? All right.
No. So no feeling calculates. I got the. Okay. That's okay. I don't know. Or like. It's weird, but you don't say the bird, but I think it's called. And then, well, not routine, it's not. I think that would be, no, it's just the way this side. It's like the bird, you just go into the right position. Oh, okay. Oh, yes. Well, I gotta check this out. Yeah, right. And let's start with the.
That's how it looks. I thought.
Okay, have a nice day.
So the second part says use this, second rate of change to explain the graph, why the graph B cannot resemble the following graph. Well, again, this graph is trying to show the actual function itself, right? By the way, does anybody know what this graph is?
Where?
No,
It's
oh, like a logarithmic.
Well, it's not logarithmic, but
the parabola.
logistic,
It's
which we'll learn more about in a moment too, because we're doing logistic differential equations. So, by the way, logistic growth and decay models, the reason why you can say it looks like logistic growth and decay is because they have an initial starting value, okay, and they have a max population you can reach. It's all about like we use logistic growth models with stuff like infections because there's a limit to how many people can get infected, right? The population. You cannot go beyond the population. But there's also a minimum value as well. Okay. So yeah, this is it appears to be a logistic growth model. But why looking at really either of my functions, um, why cannot my function, my original function, use this model? Look like this. It it's tricky, okay? Because of course it's BC. What do we have? We have the rate, right? We have the rate of change, okay? And this rate of change, my dBdt, is negative, right? My second derivative of again, that would give me the second derivative function. So my rate of the entire function is what? Is decreasing. Now, do you remember what happens when your second derivative is decreasing? What does that mean? Your function is what? Concave down. Look at your graph. There's only part of it's concave down. So that's why this graph cannot be used to represent my function. Because only part of this graph is concave down. So the answer is, since d squared b over dt squared is less than 0, okay, when 20 less equal to b less equal to 100, meaning the given graph should be concave down.
Well, actually, I would say.
Okay. This graph has a section that is concave up.
Oh, so my question, you multiply -1/5 by dB/dt for the same reason that you multiply like x and you multiply y by dy dx when you're doing.
Say for the same reason, what is dB/dt? It is the rate. It is the function that is describing the rate. It is not the function itself. It is the function describing the rate. Okay? D squared b dt, okay, is looking for the function that describes the rate of the second derivative. Okay?
So you got to.
So we're going to take the function, we're going to take the derivative of my rate function, which we just did, we got -1/5, and then multiply it by the rate function, which again would be my function that describes the rate of the first derivative. So I multiply the two together. Yeah, this you can understand. It takes some time to process. All right, because again, we're not dealing with just functions, we're dealing with rate functions. Okay, or differential functions, which again, it's the same concept. Rate functions and differential functions, same thing. They cannot be treated as just traditional functions. All right, part C. Use separation of variables to find the function, the particular solution. So basically do what we've been doing. All right, so we have dB/dt equals, I'm just going to 1/5. I'm just going to distribute that. 1/5 of 100 is 20 minus 1/5 b. So that is going to give me that. No, let's not do it that way. because I'm going to have to put that in our denominator, and I don't want to do that. So we have 1/5 of 100 minus b. So multiply by t, divide. I'm just going to divide by this. So I'm going to write this as 1 over 100 minus b db equals 1/5 dt. So when we do the integration, we are going to get the negative natural log of 100 minus b equals 1/5 t plus c. It is, I mean, even though we do know my b value is, my initial b value would give me 20. So, yeah, all my values are going to be positive anyway. So I don't, because I know this is modeling a real world situation, I'm not going to have a zero value for weight ever. Okay, it's fine. It doesn't really matter because you're going to get rid of natural log, right?
Why would it be wrong to say, for the right side of the equation, that it's ln of 5?
It wouldn't. It would just cause more of a headache. Yeah.
Get back to is not.
Yeah.
When we do.
Yep.
But
Now, to make it a bit easier, what would you do to the negative? Yeah, so we get the natural log of 100 minus b equals negative 1/5 t and plus c, because it really doesn't make a difference what you do to the c.
unless they give you.
Yeah, and then what matter? So now we have, if we take e, raise both, again, you can think of it as just using both of these as an exponent with base e, or what's called the equivalent exponential exchange. I don't know if you remember doing that. But 100 minus b equals e to the negative 1/5 t times ec, or again, what we wrote as a. So negative b equals a e to the negative 1/5 t minus 100. And then we are going to change all the signs. Actually, we can leave it alone. It's fine. You don't have to change the signs right now. Because right now I want to find the value of a. Yeah, at the end. Right now I just want to find the value of a. So they said when t is 0, b is 20. So
So we need to solve for the demand. So we don't, will we put a negative sign in front of it or no? Oh wait, we would at the end, wouldn't we?
so that gives me that a is 80. So b is 20 when t is 0. When t is 0, that just gives me e to the 0, which is just 1. So a times 1 is a. So negative 20 equals a minus 100. Add 100 over, a equals 80.
Wouldn't that be one, oh wait, is that negative one? No.
It was, yeah. I just left it as negative for there. So we do know that negative b equals 80 a e to the negative 1/5 t minus 100. And if you change all the signs, you get b, or b of t.
Okay, how much?
Minus 80. I don't need the a there. I don't know why I put the a there. E to negative 1/5 t. Now in this case, t does have to be greater than or equal to 0.
That's because you can't have negative time.
All right, we good? Next page. All right. Logistic growth and Euler's method. We probably won't get to Euler's method today, but I'll have to get to some logistic problems. All right. Now, logistic growth difference equations. A population often increases exponentially in its early stages, but levels out eventually as it approaches a carrying capacity because of limited resources. A P of t is the size of the population at time t, then dp dt equals kp for a small population. But actually, the relative growth rate decreases as the population p increases and becomes negative if p ever exceeds its carrying capacity k. So, k is the max population that the environment is capable of sustaining. Logistic differential equations is given by dB dt equals kp times 1 minus p over k. All right. Now, as p approaches 0, then dp approaches
Yeah.
Oh.
1.
which again would be 0, but because p is approaching 0. No, it wouldn't be 0, would it? Yes.
Also the 1.
Mhm. So as p approaches k, then dp or dt approaches 0. Yeah, this is a different k here. Lowercase k and capital K. And that's fun. What?
So totally, or is k mean two different numbers? Are they two variables? Because it's over here, it's saying that kp is one thing.
Well,
So.
it's similar to what we just had over here. Okay. That,
The qt stuff.
yeah. So very similar to what's over there. The difference here is we have a max value that we cannot exceed. Okay. They just it's a poor choice of letters, I think, using capital K and lowercase k. So yes, those are two different Ks. Capital K, and I say carrying capacity, capital K is the max population the environment is capable of reaching or sustaining. Lowercase k is more about the rate, the actual rate.
Is that like the proportion, or is it a different?
Yeah. Rate, proportion, There's well, proportion actually stands for the fact two rates are equal to each other.
Oh,
All right. In real world terms, this means for a small p, the population increases at a rate proportional to the population at the given time. Right? For a population close to its carrying capacity, capital K, there's distinction, the rate growth is close to zero. So, just to give you an idea, that's why I said that this graph here did look like a logistic growth model, because as a small population, the rate of growth is pretty small. As the population grows, the rate grows bigger and bigger and bigger and bigger until it starts reaching what? Its max capacity. Then that rate of change gets closer and closer to zero.
so it's kind of like an exponential function with like limits as higher.
Yes. All right, so what happens when P is greater than K? In this case, it'll have a negative growth rate.
Now, does that mean it's slowing down, or does it mean that it's actually reversed?
That means that it is actually decreasing, yeah. At that point, again, it's a lot of things that go into that. Because you have a max carrying capacity, you should see that rate decrease and then kind of fluctuate almost. Because then as it goes back down, then it will, keep kind of fluctuating. Um, and it's so minuscule though that it still looks like it's a zero. Right. Which time we get? We got plenty of time, huh? Yeah, we're doing good. Population of deer, P, is modeled by a logistic growth model where K is equal to 0.08 and carrying capacity of capital K is 1,000, where T is measured in months. So write the differential equation. Well, dP over dt equals K, which is 0.08 times P, of 1 minus P over 1,000.
Yeah.
I sketched the slope field from your calculator. Okay. Um,
I thought calculating you can do something. I was from building.
Well, if they could, but like.
one. Trying to figure out what it means. Let's see here. Let's plug this function in. So 0.08, x of 1 minus x divided by 1,000.
That's not saying, okay, I was thinking that was. You too? Oh, yeah, it's 118. Wow. I don't think it's. That's basically our last result was from. I don't want that. Yeah. And then there's no days off after spring break.
What this is, again, this is the, again, since I can have a population less than 0, I do have to start at so
It's just.
this graph. Now, this is not the graph you're going to graph. Okay. No, this is the equation of the slopes. So what they want you to do is sketch the slope field of the actual function based off this graph. For logistic growth models, because again, we cannot have a value less than 0. Right? What this tells us is anything at 0 and beyond is going to have, well, a 0 slope, or can't have a negative, but yeah. I'll have a negative slope after it reaches its pop maximum. Okay, but we cannot go less than 0. So yeah, right here we will have slopes of 0, basically everywhere.
So.
So yeah, everywhere over here slopes of 0. Now, looking at your graph, where do I have the highest rate of change?
I can see that in this one. At 1,000.
This is the graph of the rate of change. So what's my highest value? 20 at what? 500. So at 500, so we'll go by 100. So 100, 200. Wait a second. A second.
You missed the variable.
So,
Everything I did.
or also a slope of 0.
There's nothing going to be down there because you have a horizontal asymptote. We can't go below 0 in actual population.
Wait, but wouldn't that be the same case for quadrant 2 then? Why did we put lines in that?
This is really true. Don't have negative time either. Yeah. Now I think I'm having a little issue because I'm putting the population down here and it should be time.
Now. These spots.
No. This looks like at time equals so let's know the point of interest is halfway between 0 and k. This is when the population growth is the fastest.
The last time we talked was November 19th, 2021. Access jar? Yeah, and I was like, I was sort of saying, asking, like,
Let's go ahead and do part C before we get to this, because honestly, it'll be easier to find the equation and show you where the equation comes from if we actually have the function. So, draw a particular solution if the initial population was 100 deer. Okay, so we know dp dt equals 0.08 p1 minus p over 1,000. All right. So we're going to get 1 over e times 1 minus 100 dp 0.0 dt. Yeah. All right.
without having limited,
Not
I'm saying wouldn't it be other,
so yeah, it would be, but you'd have to account for something else as well. The chain.
Why need your thousand? I think it's gonna be. No, they posted every spell but mine. Really? Yes. I don't know, because they take it like on Instagram app. They literally looked at it and clicked that. No.
Read this question wrong because it says draw a particular solution, not find the particular solution. All right. Let's look at this back of this graph.
We're gonna get it going.
So, looking at this graph, let me draw this graph. Looking at this graph, we have at 0, we have 0. At 500, we have our max. At 20, and then back here at 1,000, it reaches its, back to 0. Okay. Now, what is the horizontal asymptote here?
So 0.
That is DP, right?
What is DG?
The rate of change of the population, right? Because VP over DT is equal to the function we just typed in. And this is DT, right? Vertical asymptote DT. Sorry, the axis. Horizontal axis is DP, the vertical axis is DT. So that means that dP over dt is 500 over 20. Gives me about 25. So halfway through this, okay, halfway through this, my highest rate of change should be about 25. Okay, so I'm not going to put any values down here because I don't know what exactly the time is. Equals. So as I progress, my slopes should be increasing until it gets really severe, somewhere halfway between this, about 25. Really severe. Once it reaches that halfway point, say halfway, it starts to go back down until it reaches what again? 0.
Wait, wouldn't the line?
This is what I mean is what we're doing here is we are creating the slope field of the actual function. It does not have to be perfect. Now it says find the initial value starting at 100. So if we start at, let's say this is 100, 0, as we progress, it should get what? More and more severe until it starts to decrease again.
Oh, right.
And then right here should be that 1,000 mark. I'll have to look at doing this one because creating the actual function is going to be real fun. Okay, no, ask away.
Is that like the slope field of the original equation and then like your little parabola that and then you have the derivative of it? Or is it the other way?
In red would be the slope field of the actual function, not the derivative function, not the dp/dt. We did not do the slope field of dp/dt. We used dp/dt to find the actual. Yeah, we had the rates, so we had the slope of each value.
Then it like it increases the essentially.
Yeah, so the slope should all the slopes are positive everywhere, right? So all the slopes are positive everywhere until we get to 100. Once we get to 100, again, it does go back down, but technically we still use that as an asymptote.
You said technically like what?
Technically, the slope would be negative after 1,000, but we still use that as a zero asymptote because we would never reach it. So the slope would get so small the closer we get to my max carrying capacity that you've never actually reached 0. It's kind of like that old riddle. How long would it take you to reach the endpoint if you kept jumping halfway to it? You'd never get there. So yeah. Part C is the blue line. All right, we are going to pause here because we have like 3 minutes left, I think. So